First of all, I want to say it's been great being here. I'm been here for 3 weeks, 4 weeks tomorrow, actually. I'm here for another month, traveling around to Perth and Sydney. And had some really nice discussions with people. And when Ilya mentioned that there was this follow-up meeting following the TDU, I thought, well, I could talk about one of my long-standing loves is how ANITA limit can actually drive a very large mass loss. But then I heard all these great discussions at the school about tidal disruption events. And so I'm going to focus on a really kind of follow-up to Daniel Price's talk about how you can actually drive these outflows that you infer for tidal disruption events. And again, there's thanks to all those people on the bottom that have had some great discussions. I'm new to this field, and so I may have some things wrong, but hopefully there'll be some new interesting perspective from somebody that's outside. So this was a slide from Katie's talk at the school about the idea. We already heard some about this, about the jet going out the poles, and then you have for these tidal disruption event, you have all this outflow, maybe a disk and so forth. And the key thing is that when you're looking, well, at least when you're looking through this dense outflow, you're basically seeing optical and UV light. And so there's a lot of reprocessing going on, at least in some of these cases. And the other thing I want to point out is that you see these emission lines of H alpha and helium. And basically those are very broad, and they're telling you that there's something flowing at very high speed, about 10,000 kilometers per second. And in principle, you could use those strength of those lines to infer something about the mass loss rate, but I'm going to talk about a much simpler approach. So the basic idea of a wind photosphere is that you have a wind that's so strong that you can't see through it. So you can think about integrating the optical depth through from some radius to infinity of kappa rho dr, the standard just definition of optical depth. But for wind, if it's constant velocity, then the density is just m dot over 4 pi r squared v. And so the only thing that varies, assuming the opacity is fixed, is just r, and that's really simple to integrate. And then if you want to solve for tau equal to 1, it's just basically gives you a photosphere. And as Daniel mentioned earlier, this is many AU, that the sun is about 200 AU. The sun's one AU is about 215 solar radii. So this is about 100 AU. And it scales with those parameters where mass loss rate is in 1/10 of a solar mass per year, and the flow speed is in 10,000 kilometers per second. But now you can just use the Stefan Boltzmann law. We all learned in undergraduate astrophysics to basically then derive what a temperature would be like of the material at this photosphere given the luminosity. And it has this scaling about tens of thousands of Kelvin for those parameters. So basically, you very easily can reprocess the light that's coming out from the central engine. The key point here is that you're huge solar luminosity, something like 10 to the 10 suns. So the fact that this is a temperature of a hot star, as Daniel said, this is like a ginormous O star with 10 to the 10 solar luminosities and a massive core, except by the black hole, maybe 10 to the 6 solar masses. So the question, this is the key result, is that you basically find this simple relationship between the temperature that you see and the mass loss rate. And the question that we want to ask now is, can such mass loss in flow speed be explained by a super Eddington wind? So this is another slide from Katie's school talk, that when you look at the X-ray bright tidal disruption events, you see both super Eddington and sub Eddington things. But in the middle, there's this gap, and these guys are all filled in with optical and UV bright. They're basically X-ray dim. And so these are prime candidates for having this reprocessing. And there's the Eddington luminosity over here. You can see these things are all very close to the Eddington limit. And these are their luminosities in solar luminosities, log of the solar luminosity. So what are the requirements to have a wind? Well, first thing, you have to overcome gravity. The flux-weighted mean opacity has to be greater than, times the luminosity has to be greater than the Eddington luminosity. So that's one thing. That's kind of like saying if you want to launch something into space, you got to overcome gravity. So if you want to launch something in space, you got to take the. And it's relatively easy to do that, but what's hard to do is to make it so it doesn't, that it makes all the way to orbit or to escape. So the other thing you have to have is the energy. you have to have the energy. So there's a relationship between potential energy you need to lift a wind and the luminosity that you have available. And I call this the photon tiring number, because as the photons do work to lift the gas, they're going to become less and less energetic. Anyway, those are the parameters for that. So those are the key ideas. So now let's just back off and do a little bit of basic hydrodynamics. This is steady state acceleration of the flow is equal to the radiation force outward minus gravity. And if you then just convert that into Eddington notation, then you find that the acceleration is just gamma minus 1 over gravity. And this just means that if gamma is greater than 1, it's like an anti-gravity. If right now we had some radiation force on us that we're propelling us away from the Earth at twice gravity, then we would all fly away from the Earth and reach the escape speed of the Earth at our terminal speed. And so I think this is like anti-gravity. But what's more, you can then just multiply the same equation by the mass loss rate, and is 4 pi r squared v. And then write the dr on the right side, you find that it becomes like a comparison between the change in velocity and the change in optical depth. So you can integrate that equation. You find out that the momentum that you put into the wind is proportional to the optical depth times the momentum of the photons. So if you have just a tau is over unity, it's like a single scattering limit. You're limited to just L over C. But if you scatter the photons many, many times, you can get more than that. So Wolf racers, for example, have this kind of performance parameter of about 10. But then if you then say, just for simplicity, you assume gamma is equal to 2, you say gamma is equal to 2, then basically the terminal speed will be just equal to the escape speed. And now the total energy requirement is just m dot v infinity squared without the factor 2, because you're covering both gravitational potential energy. And that basically tells you can't get this to be too optically thick. Otherwise, you would just photon tire. You wouldn't have enough energy to sustain the flow. The flow would actually have to slow down and stagnate. And I've done a lot of work on this photon tiring limit. All right, but now how does that apply to tidal disruption and super Eddington winds? Well, again, if you assume this just simple case of gamma equal to 2, then you find out that you need to be twice Eddington. That means you have to have, for 10 to the solar mass, 10 to the 6 solar mass black hole, you have to have about 8 times 10 to the 10 solar luminosities. But then if you plug this in, you find out that it's just marginally optically thick for these typical scalings. Basically, it's going to have multiple momentum, but the amount of energy is only about 10%. So there's plenty of energy to propel this wind that you're inferring from observations by the optically thick envelope. And bottom line is, it works. How about that? And so the takeaway here is for the inserted supermassive black hole masses of about 10 to the 6, the Eddington luminosities, about 4 times 10 to the 10. If you can get twice that, if you can just get a little bit above that, you can drive a wind easily. Now, what it means is that you're driving the wind from someplace where the escape speed is of order 10 of the wind speed. So that's going to be someplace around the black hole, not right down to the black hole. Because after all, a lot of the energy that's potentially coming from the shock that Daniel talked about earlier. So you have all this energy you put in a certain radius. You're still deep inside the gravitational potential well of the black hole. That then energy then propels material away in this outflowing wind. And then that's the reason that you basically reprocess the X-rays into optical light. So that's the bottom line, a preliminary result. This is all stuff that I just did in the last couple of days. So I might have some details wrong. But one of the great things about coming on a visit like this is you get to apply the stuff you've worked on all your life to a new problem. And this seems like a really good. Now, I'm sure there's lots more details that need to be filled in, but the bottom line here is that this kind of works. It's pretty cool. So I think before I finish, I just want to do one shameless plug. Is that you might tell I love to teach, and I've been teaching a course called Fundamentals of Astrophysics, and I have a textbook that it's much more basic than this stuff in here, but it's as you can see, I really like to focus on the fundamentals. All right, thank you.
Great job, Sam. We have 10 questions. While people are looking at questions, I'll ask one, or maybe even two, but okay, I'll start then. So if I may. One question is, it seems observationally that the photospheres may be even a little bit further out than what you had found. So I think you found them to be at around
180 years. So.
Oh, I thought it was a little bit smaller. I thought it was a
No, it's basically 2,400 solar radii.
okay. So 10 AU, right? Yeah, I think it's about
No,
10 AU. Yeah. It's about 10
I'm
AU.
sorry.
Okay, so you found it to be about 10 AU.
Yeah, 100. That divide that into 100 is like, yeah, it's about 10.
Yeah, it's about 10 AU. Yeah. So I think they're actually they may be tens over U.
Okay, but this is the back of
might
the.
have to say
It's
that
the back of the.
it's higher a little bit.
Right, that's just a canonical number.
Okay.
Yeah, but then I think the point is that you're just tearing apart you're tearing apart a solar mass star, right? Supposedly the star that's getting totally disrupted or favored to be around a solar mass. So you can't, and then some of that's going to be going into powering accretion and the shock and so forth. So the efficiency can't be too high. And so if you're going to go, you think you can run into energy problems if you start making the massless rate, because if this thing lasts for a year, then you can't have a mass loss rate that's too much more than this.
I'm just thinking in terms of observationally, we see these things rising relatively slowly for transients. How long would it take for like this to switch on after the debris?
Well, it's the kind of time scale that Daniel was showing in simulations this morning. I would say on the order of a month or so. I mean, a lot of it depends. The rise time, if I understand correctly from the the traditional model, the rise time is proportional to the black hole mass, and so it depends a little bit on that. One of the things I would say is that this diagram here, would be really nice if rather than just have, since this is supposedly the time over which the event is evolved. And it's supposed to be a proxy for mass. It'd be nice to just make the Eddington luminosity go up there. And you can see there's a bit of a trend. I mean, you're focusing on a very narrow band here, but if you spread that out, there's a bit of a trend where the longer lasting things are higher luminosity, which says that they're probably above the same amount above the Eddington. Right? So I actually asked this of Kate in the talk in the school about, why don't you plot this as a slanted line rather than a bunch of horizontal lines? Because if you think that there's a relationship between the mass of the black hole and this time. Anyway, that's a key point. The time scales are given here in seconds, but 10 to 7 seconds is a year. So the rise time is about a year. And then after that, then there should be, that's when you start to have the self collisions that Daniel talked about. And then you start to form this sort of transient stellar O star, super Eddington O star.